Welcome back, everyone. This will be the part 5 of CUDA programming series. This particular video will not uh, have any code for a particular kernel, but we will be looking at GPU architecture and how it works. So there are multiple images. All of them are taken from the book called Programming Massively Parallel Processors, and we'll go through them one by one and try to understand what they are trying to convey, and then see where we go. So there will be no code present in this video. It is just theory, but it is essential for you to understand how these things work. Now, as a CUDA programmer, it is very important for you to understand the architecture of a GPU, how it looks like. So each particular GPU is having a multiple something called streaming multiprocessors. Let me write it down. Streaming multiprocessor. So if you look at the particular hardware description of a GPU, you will see that they describe the number of streaming multiprocessors required, and each streaming multiprocessor comes with a bunch of cores, GPU cores, which we can say as core here in short. So you will see that there are multiple streaming multiprocessors available. Each of them has these green cores, and these cores are highly threaded. And these streaming multiprocessors also come with their on-chip memory as well. So each SM will have their own memory, they have control logic, their own ALU, their own cores, their own registers and everything. Then there is a mechanism for loading and storing the data from global memory. So this global memory is also, let's say, just for the ease of convenience, it's also called DRAM. It is generally in the size of gigabytes. It is pretty big, and you will observe that this particular DRAM memory is far from streaming multiprocessor. So it is big in size. Memory is big, but the latency to get the data or read from it is pretty slow. Whereas the memory available on chip on streaming multiprocessors is pretty fast, but it is also slower, also smaller in size. Now, each streaming multiprocessor works like this. So whenever you invoke a block of threads, each block will get assigned to some sort of a streaming multiprocessor. All the threads in a particular block. So this will have, let's say, n number of threads. All of these threads will get assigned to one particular SM simultaneously. They will be simultaneously assigned to one single SM. All of those threads in a block. So it won't happen that thread 0 in a 1 in a block is in SM1 and thread n is in SM2. It does not work like this. All of the threads will be assigned to the same particular SM. Now, it can also be the case that there are multiple blocks that you are invoking, which is always the case. And a lot of those blocks can be assigned to the same streaming multiprocessor. So you will observe that this in image. So there are three blocks here and three blocks here. They're getting assigned to an SM here and another SM here. You need to know that there are a limited number of streaming multiprocessors available, and there is also some sort of a limit to the number of blocks that we can try to assign to some sort of a streaming multiprocessor. Now this limit is already defined on the architecture review or overview of a GPU, and we need to take that into consideration while we are calculating the occupancy. So occupancy would be a new term for you, but basically it is maximum number of threads available. Some people say maximum number of warps available, but it is the same thing. It is multiplication of 32. So numerator and denominator gets cancelled times 100 and active threads. So if something has 100 threads as the maximum number allowed, but you are using only 75 of them, you have 75% occupancy, and there is some chance to improve that or utilize the GPU further. you need to remember that threads in the same block are assigned simultaneously or scheduled simultaneously to one particular streaming multiprocessor. It is an important fact to know before we move on to synchronization. So in the earlier videos, we have already seen how do we do synchronization. We do it using this keyword sync threads. So this is a barrier synchronization which allows this ensures that the threads in one particular block, they have completed, let's say you are doing some sort of operations and then you are using sync thread here. So this makes sure that all of the threads in a block that are assigned to a SM complete all of these operations before moving forward. So you can understand it better from this diagram. So these are the threads assigned to a block. They belong to one single block, and this is our barrier. And in our case, it is sync threads. When we say we are implementing a barrier, we can assume that there will be some threads, for example, n minus 2 in this case, which will complete all of the operations first. And there will be some threads which are lagging behind. This is just how parallelism works. Now, introducing a barrier will say that, hey, thread n minus 2, before moving forward, please wait for all the other threads to complete their operations. And after all of the threads have reached here, only then we can move forward with other operations that are scheduled after the barrier synchronization. Now, if we have a sync thread statement in an if block, it needs to be executed by all the threads in a block. Otherwise, what will happen? Let's see. If you have some condition here, some else condition here, and both of these have their own sync threads, you may assume that these sync threads are the same barrier synchronization, but it is not true. They are different synchronization threads or barriers that we are putting in our phases or operation of a particular thread. But these are two different barriers. So you need to remember that. These are two different barriers, and this will result in path divergence. The some of the threads will take this path, some of the threads will take this path, and these will be two separate barriers. So suppose these are the threads doing operation. First sync thread can be this barrier, second sync thread can be this barrier, and this does not make sense. This will always result in undefined output. So please make sure when you are putting sync thread in some sort of if or if else statement or a for loop, you need to make sure that all of the threads um, pass through only one sync thread, not the second one. So it can be like, suppose you are doing a condition if thread ID %2 equals to 0, then a sync thread 1 will be applied, else another path will be taken, and we also have written sync thread here as well. You cannot do that because half of the threads, if there are n threads, half of them will follow this path, half of them will follow this path, and this will reduce the parallelism by a lot, and all of these sync threads are different barriers. So you need to understand that incorrect usage of a barrier synchronization, it will always result in an incorrect result, and it can also result in a thread lock. So what is a thread lock? Sorry, a deadlock. Apologies for that. It can also result in a deadlock. So there can be some threads which are waiting forever to complete their operation. So to avoid deadlock, avoid going into that particular problem, make sure that if you're using sync threads, all of the threads reach the same barrier. Sync thread should be the same barrier for all the threads. It should not be different. So all the threads in a particular block, we already know they are assigned to the same streaming multiprocessor. They also need to be assigned to the streaming multiprocessor simultaneously for this task. So this allows in scalability and everything. But no need to worry about if you don't understand it right now. Now, when do we need to use a barrier synchronization? So it should be used whenever we want to ensure that the threads in a block, they should complete all previous phase of their operations that they are scheduled for before they start the next number of operations. Moving on to the next image. In the earlier videos, we have already seen what a warp is. So when we assign a block to a string multiprocessor, a block is further divided into a group of 32 threads, and each of those are called warps. So till now, the current architecture of NVIDIA GPUs is such that a warp is of 32 threads. It can change in the future, but we do not know for now. Now you will see that there is a block one assigned to, there are three blocks assigned to this particular SM, and each block will have a lot of warps, each of 32 threads, and these are assigned to this particular single multiprocessor, streaming multiprocessor. Pretty easy to understand. When we are invoking a block of threads or a grid of blocks, each block is further divided into a group of 32 threads. Now, if a block has only, let's say, 17 threads, the system will always pad the last remaining threads to complete the number 32. So we will add 15 inactive threads here. Pretty easy to understand. Moving on to next. Now, this is very easy to understand how it will work when your thread have only one dimension. So if, let's say, again, just moving on to the example, if they have only 17 in x direction, then they can pad 15. How do you divide which threads to go in which warp if you have two-dimensional threads? Let's say this is T00, T1, yeah, it is T10, T20, T30, and so on. This is TNN, T33 in our case. So we will first assign them linearly or write them linearly. So T00 all the way to T01, 03, sorry, will go here. Then T10 to T13 will go here. Then T20 to T23 will go here. Then T30 to T33 will go here. Now we can decide 32 groups. Now you can pretty easily divide this group of threads or a block of threads in 32 groups, and each of them will be a warp. Same goes for if we add a third dimension through these threads as well. Now, our streaming multiprocessor is designed such that it has to execute all the threads in a warp following a single instruction. So all the threads in a warp, they execute simultaneously. They are executing same instruction at the same time. So this is time. They are at the same time and for executing the same instruction, but they are on different data or multiple data. So they follow something called SIMD, single instruction multiple data. Uh, so the SIMD hardware is such that it restricts a thread in a warp, and they have to execute the same instruction at a particular point of time. This behavior is also called a single instruction multiple thread instead of multiple data. So you have single instruction, but there are multiple threads that are executing that instruction at that moment. So we have already seen how this works. If you have a block of 4 by 4 threads, you need to first write them in linear order and decide them by dividing into the 32 blocks. Now this is an important part, uh, something called control divergence that you need to understand. So the SIMD execution of threads, it works very well if all the threads within a warp, they follow the same execution path. So they should not diverge into one path and another thread should go another into another part. They should not work like that, and it always um, impacts the performance very poorly. So this is called control flow when we are working on the data. So if we are in a warp and all of the threads in a warp, they follow different execution paths, we say that we have reached something called control divergence, where a group of threads will follow in this image A, another group of threads will follow B. And we will understand what the diagram on the right means. So there is a cost to divergence. So there are extra passes that the hardware, in our case GPU, that needs to make, so that all of the threads in a warp, they are able to make their own decisions, and they take their execution resources along with them as well, which impacts the performance. So in this image, you will see in the first line, all of the threads will arrive simultaneously, will execute same instruction simultaneously. But when we are here at A, some of the threads which are less than 24 in TID will be executing this path, but all the other threads will remain inactive. But when we are in B, all these threads will remain inactive while these threads will be active. And when we are C, again all of them will start working again together. So you will see when we are in different paths, a large number of threads remain inactive if we are allowing control divergence in our kernel. So it is very important to not allow control divergence, but it will be difficult to do always. But we need to take cognizance of the fact that it will be there, but we need to minimize it somehow, writing the ifs and for loops in such a way that it is minimized. Now, what we need to understand is something called occupancy. As I have already mentioned the formula, the occupancy is the ratio of number of warps or threads that are assigned to an streaming multiprocessor divided by the total number or maximum number that it supports. It is called occupancy. So in a streaming multiprocessor, it includes a lot of execution resources that it comes with, which includes registers and shared memory as well, thread block slots and thread slots. So all of these resources are there. So it is pretty difficult to understand how changing just one thing can impact the performance by a lot, but you can have a very rough estimate of how it is impacting it. So there is one example in the book. I would like to tell that here. Suppose we are writing a kernel that uses 31 registers, right? 31 registers per thread. And we are configuring the kernel such that it has 500 threads per block. And in this case, let's say the maximum number of threads that the string multiprocessor can have is 2048. So maximum number of threads. So the number of blocks we are invoking is 4. So total number of registers we will have it hand is 4 into 512 times 31, which comes out to be 63488 registers, which is fine. Now suppose if the GPU architecture is such that it only allows 65336 registers per SM, there is a limit to the number of registers you can have. Now suppose we just added two variables in the kernel, and now the number of registers that it requires moved on to 33. In that case, the total number of registers it will require for the same structure is 4 times 512 times 33, and it comes out to be 67584, which is much higher than the limit, and the streaming multiprocessor cannot allow it because it does not have enough resources to sustain this operation. In that case, what it can do is only have 3 blocks. When we are using 3 blocks, we will invoke only 3 times 512 threads instead of 2048. What is the occupancy? 75%. So just by adding two variables, they can be like this, int a something, int b something. We are using two registers extra. And this only this particular change reduced our occupancy from 100% all the way down to 75%. So it is very important to profile your code using tools like NCU and Nsight and understand what changes you are making in the code that is affecting the occupancy in a lot, because the cost of running a GPU is expensive. You need to utilize a GPU in such a way that you are at least utilizing it to the fullest as per your capability of writing a kernel. So that was it for this video in short. I hope this was instructional, particularly this example. So the chapter 4 of the book has a lot of good examples to calculate the occupancy. You need to go through the exercises to understand how it works. but it is pretty easy to understand what the chapter is trying to convey. But it is one of the essential parts of your programming journey in CUDA.